Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today video session we're going to focus on solving problem of quiz 5, and as we know the problem was taken from our textbook, and it's known as problem 5.41. So that's what we're going to do. And I would like to say thank you to those who already submitted the quiz answer, and then from your effort, I'm sure now you can compare your solution to what going to be shown here, and then from there you might learn something, or maybe you can send me a message saying that I can maybe what I'm doing here is slightly wrong, so maybe you can give a comment, and from there we might have a nice discussion, or we call it academic discussion regarding this problem. Okay, so what this problem all about? So what given in this problem is that there is a dielectric interface. Okay, so what is meant by dielectric interface? Just a boundary. So I'm going to denote that as this simple flat line. Actually, this is in a 2D representation. In a 3D, is actually an area. Okay, so this is what we call it to be dielectric interface. And then given the equation to represent this dielectric interface, then the equation given in the problem is 4x plus 3y equal to 10. Okay, so from here, what needed to be defined? Region. Okay, so the interface is just a boundary dividing two regions. So to differentiate between the upper region to the lower region, I'm going to define the lower region having properties of 4x plus 3y smaller than 10, and the region, the upper region, going to have a characteristic of 4x plus 3y greater than 10. Okay, so that should be my definitions of region, because we need to do that, okay, in order to make our solution as accurate as possible. So what we are doing now, we are defining the lower region logically smaller than 10, and the upper region logically greater than 10. Okay, that's done. And then given by the question, it said origin. Okay, this is the information given by the question, origin. So for us, origin should have coordinate 0, 0, 0. Okay, and this origin is located at medium known as free space. Okay, and then this medium is labeled as region number 1. Okay, that's information is given by the question. So now, where should be our origin? Is it going to be the lower region, or is it going to be at the upper region? So we have to test it by how? By substituting values. So now we're going to use this equation. So by checking the value 4 multiplied with 0, because we now saying x equal to 0, we're going to place 0 here, and then plus 3 multiplied with 0 as well, and then the value is equal to 0. And we know that 0 is smaller than 10. Therefore, the lower region is going to be our free space region. And then we have to label it to be a region number 1. And the other region stated by the question, which is region number 2, should be dielectric medium. And then given by the question as well, the dielectric constant of this dielectric is equal to 2.5. Okay, that's should be the correct interpretation of the questions. And then given by the question as well, D1, okay, D1, which is electric field density, and 1 indicate the field is actually in region number 1, is equal to 2x minus 4y plus 6z. So I purposely changed the number 6.5 to 6 because just to make my calculation a bit easier. And then the unit given here, nanocoulomb per meter squared. So I have to draw this D in my diagram. Where it should be here? Yes, it's going to be in the lower region. I'm going to draw it to be as such. So this is going to be our D1. Okay? And then from our discussion in previous lecture, what happened to D1 when it's entering region number 2? D1 going to have the characteristic of changing of angle. So this is what the logical behavior of the field as it propagates from medium number 1 to medium number 2. We call it refractions, meaning that D2 going to have different angle to the normal compared to field D1. Okay, so that should be the expected result. So the question asks us to do what here? Find D2. Okay, that should be the conclusion of our problem. Okay, so now how we solve this problem? So what you can see here, given, so this is our solution now. So in this problem, given D1, okay, meaning that given field D in region number 1, we have to find field in region number 2. Okay, so whenever you see this pattern of question, where you given field in one region, you need to find the corresponding field in the other region. So that's the pattern of question. So what you have to do here, you need to use boundary conditions. Okay, so that should be the steps need to be taken to solve this problem, because you've been asked to find a corresponding field in the other region of the given field in the information. So therefore, you have to use boundary condition. Why? You need to transform D1 to D2. So you have to use boundary condition located here in order to do that transformation. And how many boundary conditions that we have proven in our lecture? Good. 2. So number 1 is going to be normal component. And number 2 is going to be tangential component. So logically, what we have to do then, we have to split D1 into normal component and D1 into tangential component. So what it meant by that, so we have to let now D1 consists of normal component plus tangential component. That's what it meant by that. Because we need to use normal component related to this part of mathematics, and we need to use tangential component, we have to relate to this part of mathematics. So what we must do now, we must able to divide the D1 field into the corresponding normal component as well as the tangential component. So we have to, and then we can rewrite this in more detail such that D1 here can be written as D magnitude multiplied with the unit vector plus D magnitude multiply with the unit vector. So that's what we do. We just rewrite the mathematics to make it more detailed by splitting Dn vector into its related magnitude as well as its related directions. Similarly, the tangential is represented in its magnitude as well as its direction. So that's what we are doing here. So the first task you must be able to do this transformation, we must be able to determine these components, this mathematics component. That's what we must be able to do. So what I'm going to do now, I'm going to proceed focusing on try to determine this component. So I'm saying now, I'm going to determine the normal component of D1. Okay, in other words, I want to determine what is my vector Dn1. Okay, so that's what we must be able to do. Oh, sorry about that. Wow, I didn't realize it now. Hopefully, it's better now. Okay. So, how we do it then? So first, we must be able, okay, let's write it in more detail now. Dn1 is equal to the magnitude multiplied with the unit vector normal to the boundary. So that should be the mathematics. So I must be able now to determine this component. That should be my first task, to extract the normal component of D1. I must be able to define An, unit vector. So what's An here? The unit vector normal to the boundary. So now we have to refer back to the boundary, An, unit vector normal to the boundary. Okay, what is the equation of the boundary? 4x plus 3y. Okay, so now by referring to that information, I'm going to state now where my An, which is unit vector normal to the boundary, is equal to whatever equation given there, which is 4. I'm going to add the direction now, x, plus 3 direction, and then you remember we have to divide with the magnitude, because unit vector, remember, is vector divided with the magnitude 5. Okay, that should be our unit vector. Very simple. Just extract that information for the equation of the boundary. So that's our unit vector. 4x plus 3y over the magnitude of this vector, 4 squared plus 3 squared, which is 25, square root is becoming 5. So that's done. So now I want to extract Dn1. And Dn1 now, okay, the magnitude now, I'm focusing on this part now, can be found by doing this simple mathematics. D1 vector dot with An. So that should be the logical mathematical equation we have to use in order to find the magnitude of Dn1. The vector D1, and then you have to dot with the unit vector of the boundary, normal to the boundary. So if you use the wrong information of unit vector equation, therefore your magnitude that you're going to determine here is also going to be wrong. So this is very, very important for you to be able to determine the correct equation of the unit vector of the normal component. Okay, so let's do the mathematics now. So what I'm going to do, 2 multiplied with 4 is going to become 8 over 5. That should be x dot x, and dot x should be equal to 1. 4 multiplied with 2 becoming 8. And then 3 multiplied with 4 becoming minus 12 over 5 as well. So it's becoming equal to negative 4 over 5. That should be the magnitude of our dn1. Okay. Okay, finally, we, alhamdulillah, have able to determine the vector dn1 here, which is equal to just this equation. What is it? Magnitude negative 4 over 5. And then you have to multiply the unit vector 4x plus 3y over 5. Okay? So you have to do that mathematics. Okay, and then when you do, you just multiply, and then what you're going to have now is going to become minus 16 over 5. That should be equal to negative 0.64x minus 12 over 5. That should be equal to minus 0.48y. And remember, the unit for our D still nanocoulomb per meter squared. Okay, so that should be the first task you need to do when you are dealing with boundary problem. So this is what you have to do systematically. Now, since you have done this extraction, meaning that you have able to determine dn1 an, now we want to find the corresponding d2n, because d2 here can also be written as dn2 plus dt2, because similar equation can be given to our d2. So now my task now to relate this part of the mathematics to this part of the mathematics. That's what our objective now. We want to relate this part of the mathematics, the normal of D1, to the normal component of D2. So how we do it? We're going to use the normal component boundary conditions. That's what we're going to do now. I'm going to rewrite again. So now using the normal component of boundary conditions that we have proved together in our lecture, where we are saying dn2 minus dn1 equal to rho s. Okay, that should be the one that we have proven together in our lecture. But since rho s is equal to 0, because why? In this problem, there's no information of surface charge density been given at the boundary. So we're going to make this problem solving simpler by assuming rho s equal to 0. Therefore, what we are saying now, dn2 vector going to be equal to dn1 vector. And that is equal to what? Yes, negative 0.64 x minus 0.48y nanocoulomb per meter squared. So alhamdulillah, we have able to determine this part of the solutions. So dn2, I'm going to denote that as my number 1, because I'm going to refer back that particular information in my next part of the solutions. Okay, so let's continue now. So we have, I'm going to divide space now. Okay. Now, so I'm going to determine now my dt2. That's what our objective now. So we want to determine the tangential component. So I'm going to write now what should be the solution of the tangential component of dn2 T2. Okay, that's what our concern. So I want to determine this for the mathematics now. So once I be able to find the solution for this T2, then I just need to sum with D2, then I'm going to solve this problem. So that's what we want to do now. I want to find DT2. So how do I do that? I must relate this to my DT1. So we have to determine this DT1 first, then only we can able to solve for DT2. Okay, so that's what the steps now. Okay. Okay, we're going to set DT1 now, because we need to able to find this now in order to solve for this DT2. So how do I determine DT1? Simply by doing this simple mathematics, minus D and 1. Do we agree on that? Correct? Yes. And then what is our D1? Given by the question. What's our DN1? Given also by our solution that we obtained before. So using that those two information, so what is going to be my DT1 is going to be equal to 2 plus negative 0.64. So it's going to be what then? 2 plus 0 minus, so it's going to be equal to, anyone have calculator can do that? Okay, 2 okay, so 2 minus minus, so become 2.64x. Okay, and then minus 4 minus, going to become minus 3.52 y, and finally 6. So there's no z, so I'm just going to add 6z. So remember unit here, nanocoulomb per meter squared. That should be our DT1. Okay, so now, since the boundary conditions for tangential component is given by ET1 equal to ET2. So we need to convert now our ED to be in terms of E. Okay, that's what you have to do now. So ET1 should be equal to DT1 divided with what? What medium that we are dealing in our region number 1? Yes, free space. Therefore, divide with epsilon. Okay, that should be our ET1. Okay, hence ET2 now will be equal to what? Yes, it's equal to ET1. So it's still going to be equal to 1 over epsilon naught 2.64x minus 3.52y plus 6z. Remember now the unit here nanovolt per meter. Okay, so that should be our ET2. So good. So we have to go further now. What is the concern of the question to find D2, not E2, correct? So we have to find D2, which is this term. And D2 actually consists of dN2 plus dT2. So now what we have here is ET2. So we have to convert ET2 to be DT2. Okay. And we're going to see now DT2 equal to epsilon 2 ET2, correct? Okay, that should be our logical step. So what is our E2 equal to? Equal to epsilon R2 epsilon naught ET2. And what is the value of our epsilon R2 given by the question? Yes, 2.5. Okay, so what you have to do, then you have to substitute all the values. Okay, so what we're going to have here, dt2 going to be equal to 6.6x minus 8.8y, okay, plus 15z. So unit here, nanocoulomb per meter squared. So this is our second equation that you must refer to later on. So just substitute 2.5. Epsilon naught going to cancel with this epsilon naught. So 2.5 multiplied with 2.64, 6.6. 2.5 multiplied with 3.52, negative 8.8. 2.5 multiplied with 6 is becoming 15. That's what should be the steps here. And we're going to end our solutions by saying finally D2 is equal to term number 1 plus term number 2. Okay, that's what should be our steps. Then when you add them together, so the solution here will be 6.6 minus 0.64, going to be 5.96 x minus 8.8 minus 0.48 minus 9.28, and finally 15. There's no z term in our term number 1, so therefore it's left with 15 in z direction. Please put the unit here, nanocoulomb per meter squared. Okay, that should be the solution to our problem of quiz number 5. So you have to do this step systematically, okay, in order to get accurate results. So please go through this example slowly and try to understand the steps. Sorry about the movement of the my solution here. I mean the area shown is not maybe professional enough, but that's the best I can do. Okay, so with that, I'm hoping that you always try to do the quiz question and try to submit on time, because that's going to contribute to your final coursework marks. So thank you very much. Inshallah, we're going to see you again in our next video. Assalamualaikum warahmatullahi wabarakatuh.